Hey guys, this is Lego Master 99 here today, or Duncan, and today right now, you guys are looking at the power controls to a computer. And I'm in Minecraft, and as I said, I've been working on my quote-unquote 100 sub special since I did hit 100 subs a few months ago, but I've been so caught up in things, but I finally was able to go around and start this project, and computer power controls, and let's just go ahead and just like turn around here. Oh, the lag. So this is the Redstone computer that I've been working on for the past couple months. Now, it is huge. I was about to say amazing. It is amazing, but it's huge. And the reason for that is because I didn't want this to be some ordinary Redstone computer. But if we go back here, this computer actually has 4 cores in it, as in some CPUs have more than one core, which means it allows us to do more than one thing at a time. And if we go into the back of the computer here, you can see these big orange things. This is 1 core, 2 cores, 3 cores, and 4 cores. And it took me about a month or 2 months to design and implement this in Redstone so that they are all connected together to one huge interface. And this was a pain to build, I'm telling you. And it has 20 lines of code, but this can be expanded all the way up to 31, and that is as much as these wires allow. So you can expand it more, and I probably will. But I just finished it, and I'm not done debugging yet, but I'm still working on it. But I just wanted to show it to you guys since I didn't want to delay the making of this anymore. So the specs of it, there are 4 cores in the computer. Each core can do addition, subtraction. Let's see here. See if I can find it. If we go down here, I'll show you the different modules. So this is the addition module right here. So this adds. The subtraction module is over there. You can compare two numbers. That's up here. And then there's bit shifting left and right, which is, if I can get to it, here and there. And then you can just not or invert all the signals, and that's here. And each one of these 4 cores has that capability. As I said, though, I'm not done debugging yet, so I'm not sure if it works or not. But this computer has 15 bytes of RAM, which is down here. And it goes all the way down here. And this is dual read memory, so we can write 1 byte of memory at a time, but we can read out 2 bytes of memory, which makes this computer faster, since this thing needs speeds. It's very slow. But it has what I like to call the pip and pop ports, so parallel output port, pop, and parallel input port, pip. So basically two, they're like USB ports. They're ports, and then you can connect devices to each one of these ports so that you can program the computer to send signals out and then do some like computation. So let's say you had a square root extractor or a line algorithm device that was over here. You can send signals to that, have it compute, and then input back in here. And that's all implemented. Let's see what else. There is a raw binary display here, so you can send signals to go to the raw binary display, or the 3-digit decimal display, which is a 7-segment BCD to 7 segment here, and that can go up to 0 to 255. And let's see here. Each of the cores has what is it? Shift underflow and shift overflow detection, and that's pretty nifty. You can set up conditional branches and stuff. And speaking about that, this has a conditional go-to system, which is right over here. Or there's this is one of them. So you can set up, I think it's 11 or 12 different conditions to test for each core. And each core has its own, as I like to call it, control unit. So if we look over here, I'm not trying to make this complicated or anything, but if we go over here, usually a normal computer only has one set of program memory where you program your programs, but this computer has 4, one for each core, so that I didn't run into any problems with like instructions and stuff. So then there's 1 here, 2, 3, and 4. And each one of those has its own control unit, so the signals don't interfere. So you can run different instructions at different times for different cores. And that's the beauty of this. That's why it's so complicating. And then here's more of that. And let's see what else here. It can take user inputs. It can do a bunch of stuff. And let's see. Let's go up here. So, well, that's that. Well, I'll explain in a minute. I'm getting kind of confused here. I haven't recorded in a while, so I'm getting confused. But this, as it says, not connected. This was supposed to be a 16 by 16 display that was hardwired to the computer, but as I continued building it, I implemented this too late, and as you can see, if we go into the middle of this madness here, I'm not sure if I can implement a full hardwired GPU with all this mess here. So I just gave up on it, but I might work on another revision of this computer where I'll add that in. And also, you can hardwire this to these two ports if you want to. But it's not connected, but the VRAM is up here. I just pasted that in. So now I'm going to go over the I/O a bit. Okay, so this is the I/O, or user interface as you like to call it. This is where you'll be operating the computer most of the time. So over here is the program output panel. This is what the program will output, other than outputs to the display or the raw binary display. So you have your shift overflow and shift underflow, and that is if a number is bigger than 8 bits. Oh, wow. I forgot to mention, this is an 8-bit computer. Okay, so now that I mentioned that, if there's a number that's bigger than 255, basically doesn't fit on the bus, it'll overflow, and then that'll turn on, and then you can test things for that. Shift underflow is when a number goes below 0, since this computer does not support negative numbers. And then you have indicators here, and you can program the computer to output those when necessary. The computer power controls, this is what I showed you at the beginning of the video. You can tell the computer to turn on, put it to sleep, which basically stops the clock, or turn it off, which stops the clock and then resets everything. And let's see here. The program settings, these are one set of program settings. I've color-coded everything, so red, green, pink, blue, and light blue. So the program settings are pink, and there's a couple options here. You can clear the UI and RAM on shutdown, and you can report program exceptions to the I/O. Basically what that means is that if there's a shift overflow or underflow, you can decide whether it'll show up here or not. Then this is the clock. So this computer has a very slow clock. It's right here, so it's configurable. And all you have to do is flip these switches here. Then there's a dictionary here, so if it's 0, 0, 0, 0, that's 40 ticks, 0, 0, 1, 50 ticks, and so on. And some programs can operate at 50 ticks, some have to operate at slower tick speeds because of the massive amount of data that's going around here. But I'll just leave it at 90 ticks as a default. Now these are the core toggles. Now basically you can decide which cores you want to enable or not so that you don't have to lag. Because if you only want to run a program on core 1, you only need to flip core 1 and then wait for that light to turn on, which means that it's reached the control thing down there which enables the core, and then it'll only run instructions on that core so that you don't have to have all 4 cores enabled at the same time. Yet you can do that if you have a multi-threaded program, which means you have one giant program that's connected to the computer through all these 4 things, which can be done and it is useful. But you can use these core things, like you can use it for different, mainly you guys want to use it for different program spaces. So there's 4 possible program spaces here. So in core 1, I have a very basic multiplication program, since there's no hardwired multiplier in the ALU, which is those orange things back there. And then cores 2 through 4 have a Fibonacci sequence programmed into them, since I was debugging it earlier. But you can basically choose which program you want, by flipping switches and stuff. But if, let's say, you have a program that does 2 things at once on 2 different cores, you just enable those 2, and then it'll run those simultaneously. And here we have inputs, so you can basically input things in the computer, and you can check this in the conditional goto, as I mentioned earlier. And then some more user input, you can input this onto the bus here. And the thing about this computer is that I designed it so that there is a quote-unquote master output bus. And let's see, it starts over here, and it runs right through the center of the computer. So this gray bus right here goes all the way down. As you can see, there's a lot of things connected to it and that come out of it. And basically you connect all of your peripherals, all of your data output things and input things onto the my voice cracked, I'm sorry. But you can connect a bunch of things on there, and then that goes to the memory. If we follow it down here, it goes to the memory, which is down there. So I think I've been blabbering on enough, but there's a couple other things here. Those are blank. This is the random number generator toggle. So this computer has a random number generator, which is right down there. It works by basically having different like clock speeds. So if we go ahead and just flip the switch, it'll turn it on. And as you can see, it just like has a bunch of different clock speeds and stuff. So that's pretty nifty, and you can incorporate that into your programs if you want to. And then the clear RAM, this basically just clears the RAM. And then this button, teleport to debugger center, I'll explain later. And finally, we have line of code indicators for each core. And if we look here, there's 4 different buses that connect to the cores, and that tell you, bring all the data up here to tell you what line of code it's on. So now that I've been blabbering on enough, I'll give you a couple demos of the computer running. Alright, so the first program I will show you guys is a Fibonacci sequence program. So basically it just executes the Fibonacci sequence and displays it to that display up there. And I have this program wired on cores 2, 3, and 4, so it's the same program on 3 cores. And let's see, I can run it at, I think, 90 ticks. I'll run it at that for now, but it's super ultra slow, so I'm probably going to speed it up, but let's see here. Let's do it on core 2. So basically I'm enabling the second core, and all of my settings are correct, since I wouldn't recommend changing them while the program is running, but you can if you put the computer to sleep. And actually I'll run it at 50 ticks, since it needs to be run at 50, doesn't need to be run at a slower clock speed for now. So let's hope it doesn't lag. I'll turn the computer on, and the computer will start running, and hopefully it will not crash or anything while I'm recording, but generally it seems to be pretty lag free when you're up here in the user interface, since all of the data is being managed behind me. And if we watch down below, you might be able to see some data flowing through and stuff. Yeah, see, there's a signal, and it looks like it's being put up on a display. And if we wait here, 1. So there's the first number in the Fibonacci sequence, which is 1. Or the first one was 0, but the whole thing's zeroed out, so that's pretty much a given. And you can hear the clock running behind me. Let's see up here. Oh, that lag. And then see, there's 2. And the clock is running back here, right there. And then it sends a signal out to the computer to advance the instructions. And then you have 3. And then it'll go to 5 and 8 and everything. And let's see, it's being run on core 2, so core 2's down here. And as you can see, it's running through the instructions here. And if we wait for it, it'll pulse through to the next instruction. Oh, okay, jump back. But it's very easy to program for now, at least. And then as you can see, when we're running the computer, the line of code indicators up here. So it's on line 6 now, since 4 plus 2. If you know how binary works. And now we're on 7. Now it's 8. And then we're on line 8. And so basically it'll just add the last 2 numbers that were put into the system and then spit it out. So then that was 1, 2, 3, and then 3 plus 2 is 5. 5 plus 2 is 8. 8 plus 5 is 13. And it just came up there. And let's see, so the core 1 adders, the adder that's being worked on. So as you can see, this is the dual read bus. So if we look here, I think we'll be able to see the numbers being added together. Okay, and then that's 18, I want to say, or 21, or wait, 34, 30, so it's something, but that's the adder there. And then that data comes to this cyan bus, oh, 34. So it's speeding up. And it's a very fast program if you run it at this speed 50 ticks, which is the second fastest speed in the computer. It has T55, and then once it overflows, so once it hits 233, I think, it'll shut off. But you need to run the computer at a slower speed to be able to properly detect that because the data lines are so far. So I'm going to stop the program, or I'm going to put the computer to sleep, and that stops the computer. So if we just give it a minute to stabilize, as you can see, the chunk updates are still updating. Alright, so now that that's done, all the moving redstone has stopped moving. We can change our program settings. I'm going to give it a slower clock speed, so that's 90 ticks. And we will turn the computer back on. So wake it from sleep. Now it's 144. Now it should go to 233. But the computer is almost twice as slow now. And this is one of the slower speeds in the computer. So it's slow, but it works, at least for now, since I'm still debugging it. There's a lot of things that can go wrong in a computer this complicated. And 233, there you go. And now I've enabled show exceptions to I/O, so this shift overflow lamp should turn on in the next few seconds or so, and then the computer will shut off if we painstakingly wait for the computer to continue loading. Oh, looks like it shut off already. Guess we didn't see it, but the computer shut off. See, now it's off. So you can shut off the computer from the code interface by specifying a specific command. But it hit 233 and then it shut off. So that's the Fibonacci program. It's easy, it just adds things and then tests each time when you add to see if it overflowed or not. But now I'm going to show you guys the second program. Alright, so the second program that I'm going to show you guys is a multiplying program. It multiplies two numbers together. But as this computer doesn't have a hardware multiplier in it, you have to do the whole adding thing manually, since, as most of you guys should know, multiplication is just repeated addition. And it's a very big program. As you can see, the torches here basically signify instructions. It basically spans most of the code line here. So, let's see. So this is loaded on core 1, so we need to load core 1. And now, we'll go ahead and start the program up, and we'll start it at a reasonable 90 ticks, I guess. So let's just do an easy computation so that won't take so long. So we just start the computer. Now what will happen is that in a second, once the program initializes, it will display an indicator. Oh, there it is, computer indicator 1. Now, once that indicator is on, you would like to sleep the computer and then input your first number, but I'll show you what happens if you don't. So the indicator will turn on, and then it'll turn off, and then it'll see if you input a number, and if it didn't, it'll just loop back to the to turn the light back on again. So basically it's waiting for you to input something. So I'm gonna put the computer to sleep, and let's input our first number. So we go over to the user input panel here, and let's see, let's do 2 times 3. Alright, so let's do 2, and then as you can see in binary, and then we'll just flip the computer input 1 switch so that we can tell the computer that we inputted a number. And now we will turn the computer back on. And now this light should turn off, and it'll detect that we've inputted a number, and it'll write that number to memory. And the memory's pretty fast, but it's kind of quirky. And let's see here. Now, after a while, oh, the second indicator will turn on. So, computer indicator 2. So now this light is on. We know that the computer has acknowledged that we've input a 2 into the system, into the program. Now it's waiting for our second number. So I'm going to put a 3. Then I'm going to keep this switch on to let the computer know that we've input something. Now we're going to go ahead and turn the computer back on. And now, if this light turns off and stays off for a little while, if it progresses through these instructions, then it'll start multiplying those two numbers together, or basically just repeat addition. So it's on line 7 now, so I believe that it's accepted our second number and is now taking it, it's now multiplying those two numbers together. So let's see here. It'll lag a bit, and then it'll take a little while because the computer is super slow. But I'll meet you guys back once the program is almost done computing our number. Okay guys, so our program has just finished, or it's almost done. This here 6 is on the display, and the third computer indicator 3 is turned on, which means the program finished successfully, and the computer should shut off. Oops. Okay, I left this on, which means that the screen just cleared. But if you unflip this switch and then you'd run the program again, it would stay up there until you reset it manually. But that's the multiplying program. It can do larger numbers. Just say it takes a longer time, because basically what it does is that it adds a specific number over and over and over again until it's done. But now that that's done, those are the two demo programs that I've put on this computer for now for debugging purposes, but they work, so I wanted to show them to you guys. But this computer can do a lot of other things. Alright, so those were the two programs, the two demo programs that I've run for you guys on this computer. The computer is pretty much done, it's just that I still need to debug some things. And now that I've been rambling on about a bunch of stuff the computer can do, let's talk about the debugger center. I'm not going to go into too much detail about it, since that's for another video. But basically, if we push that button, it brings us down here, and this has a bunch of tools and buttons and stuff for us to debug our program. So I added this for people that actually want to write programs with this computer if they want to. And then this button just brings us back up to the top here. So that is pretty much it. I will show you guys how to program the computer in another video, but I hope you guys enjoyed the video. I haven't really made one in a while, and sorry if it's kind of choppy, so I haven't recorded in a while, but this is my 100 subscriber special, and I hope you guys enjoy it. I'll put a world download in the description, so you guys can mess around with this and study it if you want to for anything. But I hope you guys enjoyed this video, and I'll see you guys in the next video. Bye guys.